Okay, so good afternoon, everyone. So today my topic is using grid-forming inverters to improve transient stability of autonomous microgrid and dynamic distribution systems. So I will firstly briefly introduce the grid-forming inverter concept and its relevant control. And then I will talk about the modeling work at PNNL and how these models are validated against the source microgrid field test results. And then I will use a case study to show how the transient stability of large-scale distribution systems can be improved with these distributed PV grid-forming inverters. Okay, so nowadays, most of the grid-connected inverters use grid-following control. So through the phasor lock loop and the current control loop, they make the voltage source inverter approximately behave as a current source. So the advantage of doing this is that it can control currents directly. So it can regulate the P and Q injected to the system easily. It's also relatively easier to protect the inverters from being overcurrent. But the disadvantage is that it does not control the voltage and the frequency directly. So it cannot work in islanded mode and it cannot track the loads. So basically, they behave as negative loads to power system. So as their penetration increases in power system, the system inertia will be reduced and the transient stability will be reduced. So on the other side, the grid-forming inverter behaves as voltage source. So the grid-forming control the voltage and frequency directly. So the advantage of doing this is that it can work in islanded mode. So it does not the grid to provide the reference to work in islanded mode. And it can do autonomous load tracking. But the disadvantage is that it does not control the currents directly. So it might have some overload issues or overcurrents issues. And this microgrid concept, this grid-forming inverter concept comes from microgrid. But now people more care about how these grid-forming inverters impact the large-scale power system. So the droop control is one of the methods to enable multiple grid-forming inverters to work in a stable manner. It has already been well studied in microgrid research and validated in some microgrid test bed. But today I want to specifically introduce the overload mitigation controller that is used in source microgrid. So as you can see here, it's a very simple controller added on traditional power versus frequency droop. As I mentioned, because the grid-forming inverters are voltage sources, so their currents are not controlled. So it might have some overcurrent issues or overload issues. And this controller can address the overload issues in microgrid by actively controlling the source frequency. So when some of the sources in microgrid are overloaded, this controller can do overload transfer. And when all the sources in microgrid are overloaded, then this controller can do under frequency load shedding. Okay, let's use a very simple case as an example. Here we have a very simple system, a two-source system, very simple, right? And we dispatch the output power of A1 near its maximum generation, as shown here. That's normal, right? Because in a microgrid, you always want to dispatch your power between the sources. Okay, so in this situation, if we switch this load to on, so we can see that both in A1 and A2 increase the currents to meet this load change, and the voltage is almost constant. Because both of them are grid-forming sources, voltage sources. The voltage constant and the currents just increase to meet the load change. That's a basic circuit theory, right? But you will find that in this situation, A1 becomes overloaded because its output power exceeds its maximum generation. And this overload actually causes issues, right? If A1 is an inverter-based source, its DC bus voltage will probably collapse. If A1 is a synchronous generator, this generator will probably stall. So we need to solve these overload issues, okay? So if we have that overload mitigation controller in this system, we can see that for the same event, if we switch this load to on, we can see that both A1 and A2 increase their currents to meet this load change. And then A1 becomes overloaded. But once this A1's output power exceeds its Pmax, that overload mitigation controller is activated to reduce the frequency rapidly. So we can see that during the transients, there is frequency difference. The frequency of A1 drops faster than the frequency of A2 during these transients. And this frequency difference actually results in a change of phase angle. And the change of phase angle actually redistributes the power flow between sources, right? That's just a power flow analysis. And then we can see that after about 0.2 seconds, the output power of A1 goes back to its maximum operation, and the second source, A2, takes the extra load. So the extra load is autonomously transferred to the second source. So the overload is avoided. And from the droop curve, you can see that actually when source becomes overloaded, this droop curve actually becomes vertical. Okay, so this is a knowledge I learned when I was a postdoc at Wisconsin working with Bob. It's very simple, very straightforward, but it can solve the problem. Okay, so after joining PNNL, we are more interested in how thousands of these grid-forming, grid-following inverters impact the transient stability of large-scale distribution systems. And we have done some preliminary research under Kevin Schneider's project. So to study this topic, there are several challenges in simulation because neither the electromagnetic transient simulation or the positive sequence-based transient simulation works for a large-scale, three-phase, unbalanced distribution system. The electromagnetic transient simulation can simulate the details of single microgrids, but it's too difficult to simulate a distribution system with thousands of nodes. And the positive sequence-based simulation works very well for transmission system, but the distribution system is always three-phase unbalanced, so the positive sequence-based simulation does not work for distribution system either. So to address this problem, PNNL developed an open source software called GridLabD. So it can conduct three-phase transient stability analysis for large-scale distribution systems. So we developed different dynamic components in GridLabD. We developed synchronous generators, motors, and recently we developed the grid-forming and the grid-following inverters. So here I will briefly introduce how these inverters are modeled in GridLabD. So for the grid-forming inverter, we model them as three-phase balanced voltage sources behind the coupling reactance. So the internal voltages are always three-phase balanced, and they are connected to the distribution system through the coupling reactance, and the distribution system is always three-phase unbalanced. And for the grid-forming controller here, we adopt the third droop control because it's already been well studied in previous microgrid research. So we implement the third grid-forming control here, the QV droop, the power versus frequency droop, and the overload mitigation controller that I just introduced. And for the distribution system network solution, the GridLabD uses the kind of an extension of the current injection method. So it allows a three-phase power flow solution. And we also implement the grid-following inverters in GridLabD. So we noted that in most transmission level transient stability analysis software, the grid-following inverters are usually modeled as controllable PQ node. But based on our power electronics experience, we know that the grid-following inverters always have a phasor lock loop and current control loop. So in GridLabD, we want to capture as more details as we can. So we model the dynamics of phasor lock loop and current control loop inside GridLabD. Okay, so here is how the models are developed in GridLabD. And with the model developed, you want to know how accurate is this modeling approach, right? This is electromechanical modeling approach for the power electronic device. So how accurate can it be? So we are fortunate to have some field test results from CERT's AEP test lab to validate our models. So thanks, Bob. And here I will use an under-frequency load shedding event as an example. So as you can see here, at the CERT microgrid, we have three source energy storage and the natural gas-driven inverter-based source A1 and the natural gas-driven synchronous generator-based source B1. And we have a frequency relay installed at this load bank 4. For the contingency, we treat this energy storage as an event and then when the energy storage is tripped, both A1 and B1 become overloaded because there are no sufficient generation to supply all the loads. And then that overloaded mitigation controller I just introduced before is activated to driven the frequency down. And once the frequency is driven down and reach to the load shedding frequency, this relay detects that low frequency and trips this load bank forward. And the system survived from this under frequency load shedding. And here is the field test results. You can see that when the energy storage is tripped, both A1 synchronous inverter and the synchronous generator B1 becomes overloaded. And there are some oscillations between them. But the frequency is driven down. After about half seconds, load bank 4 is tripped by the frequency relay. And the output power of A1 and B1 goes back to normal and the system survives. Okay, so by the way, I know in many microgrids, they can do load shedding. But usually their load shedding is based on fast communication system. But in this first microgrid, if we have that overload mitigation controller, it can do under frequency load shedding. So it does not require a fast communication system. And here is the field test results. Here is the electromagnetic transient simulation. And here is the grid lab simulation. So you can see that in grid lab simulation, there is no detailed waveforms anymore, just P, Q, voltage, and frequency. But it can still capture the dynamics that we are interested in. You can see here how the output power matches well with the field test results, and how you can see how the frequency is driven down, and how you can see how the voltage looks like. So that means with this modeling approach, the grid lab is able to conduct a transient stability analysis for large-scale distribution systems, potentially with thousands of nodes and hundreds of thousands of maybe inverters. Okay, so with the model validated, let's move to a larger scale distribution system. Maybe not too large, it's a mid-sized distribution system. Here we use the IE123 node test feeder as an example. Okay, we did some modifications on this test feeder. The first thing is we assume the substation voltage is lost due to extreme weather events or natural disasters because we care about the resiliency. And there are 3 microgrids in this system, and they work together as an islanded network microgrid. In this islanded network microgrid, there are 3 synchronous generators as shown in the blue dots. And there are 6 PV inverters as shown in the red dots. They can be controlled as grid forming or grid following. And the PV penetration here is about 65% compared to the peak load. So for the contingency, we select to trip off one of the generator, and we want to see how the transients look like. Because now most PV are grid following controlled and operate at their maximum power point. So here is the simulation results under this scenario. As you can see here, the PV output their maximum power, and then when one generator is tripped, we can see a significant frequency drop during this event because of the low inertia of this small islanded system. And because this fast frequency drop, there are about 12% loads are tripped. So actually, this frequency transient response is not very good because even one generator is tripped, there are still sufficient generations for the other generators, the PVs, to supply all the loads. But because of this fast, poor frequency transient response, these loads are tripped. So we hope we can improve this transient frequency response to avoid the load shedding. Okay, so when the penetration of PV becomes higher and higher in the distribution system, people are thinking about using this PV to regulate the voltage and the frequency. But to regulate the frequency, PV, in this event, PV needs to have some reserve, right? Have some reserve. So one method is to add some energy storage, and another method is to actively curtail the output power of PV so it can have some dynamic reserve to regulate the frequency. So in this scenario, we assume the PV has about 33% reserve. With this reserve, we should be able to regulate the frequency. But the key method is how do you control the inverter, right? So one method is we still use grid following control, but we add some extra control loops, such as frequency watt, as shown here. It measures the frequency and changes output power. So it's kind of like a reversed power versus frequency loop. And we model this frequency watt function in GridFD, and here is the simulation results. So unfortunately, even we have this frequency watt function enabled, we can see that the transient response is still not very good. We can see that when the generator is tripped, there is still a fast frequency drop. And then because of this frequency drop, the loads are still tripped. And furthermore, there are some oscillations between these generators and grid following inverters. So actually the system damping is even reduced. So does not help too much. So we want to see how can it be improved, okay? So another approach, grid forming, right? People are thinking about grid forming. So here is for the PV with a dynamic reserve, but with inverters grid forming control. Here is the simulation results for the same event. As you can see here, for the same event, the frequency is much more stable compared to this grid following case. And because of this stable frequency response, the load shedding is avoided. So we don't need to worry about the load shedding. This is because of grid forming inverters are just voltage sources. They respond to any load change almost instantaneously. There is no time delays between this in this response. So as you can see here, when the generator is tripped, this PV increases their output power almost instantaneously. And then the synchronous generator is almost clamped, so its speed does not need to drop. So that's why the frequency is much more stable compared to the grid following case. And I believe many people in this room already know that grid forming inverter can improve the frequency stability. But let's look at the voltage. For example, let's look at the voltage of bus 97. So as you can see here, when all the PV are grid following controlled, we can see that the bus voltage is three-phase unbalanced, and the first phase C is almost at the border of the ANSN standard. And during the transients, during the contingency, when the generator is tripped, we can see some voltage transient here. And when the loads are tripped, we can see some other voltage transient here. So the voltage transient stability is not very good. But if we can have all the PVs grid forming control, we can see that the bus voltage are still three-phase unbalanced, but the situation is much more improved compared to the grid following case. And during the contingency, when the generator is tripped, actually we didn't see too much voltage transient here. So it looks like the grid forming control can also improve the voltage transient stability. So at first, when I see the simulation results, I don't understand why. But now I think I understand, and let me try to explain this. So when all the PVs are grid following control, they basically behave as current sources. They only inject the positive sequence currents to the system, and they do not regulate the voltage. And in this islanded system, only the two generators are regulating the voltage. So actually the system is very weak because only two voltage sources here. So because the network is unbalanced, the loads are unbalanced, so we see this voltage unbalanced behavior. And because of the system is very weak, only the two generators are regulating voltage, we can see some voltage transients during the contingency. But if we have all the PVs grid forming controlled, all the red dots in this system become three-phase balanced voltage sources behind their coupling reactance. So the system is much stiffer compared to the grid following case because we have much more stronger voltage sources in the system. So even the loads are unbalanced, the network is unbalanced because we have much stronger voltage sources in the system. The voltage unbalance is mitigated and the voltage transience response stability is improved. So here we just show the voltage of one bus. And in these slides, we show the voltage of all the nodes in this islanded system. So we can see that the voltage of all the nodes have a similar transient behavior. That means the voltage profile of the entire distribution is significantly improved by using this grid forming control. So I know that many customers, they complain that as the PV penetration increase in their distribution feeder, they have some violation issues. But I believe if we can have this grid forming controlled PV, this voltage violation issues can be avoided. And again, this is a three-phase unbalanced system. This unbalanced characteristic cannot be easily reflected by positive sequence-based simulation. And that's why we want to conduct a three-phase transient stability analysis using GridLabD. Okay, so let me make a short conclusion. So today we propose a three-phase electromechanical modeling approach for grid forming and grid following inverters for large-scale distribution system study. And we are fortunate to have some field test results to validate our model. And our preliminary research in a large-scale distribution system show that the grid-forming PV inverters can improve the voltage and frequency transient stability of large-scale distribution system. And of course, it's just some preliminary research. I believe there's still a lot of work needs to be done in this dynamic distribution system research area. Okay, so that's today's presentation. Thank you.
Questions? All right. So, in the plot showing the improvement in voltage response, here, yeah. Okay. What was the difference in the current value injected by the grid following and the grid forming?
For the grid following, they inject a positive sequence currents to the system. For the grid forming, I always assume my internal voltage are three-phase balanced, so the currents is just decided by the network. Of course, they are unbalanced, but it depends on the system, the network situation, right? I just guarantee my internal voltage is three-phase. I didn't show them, but here I just show the real power, right? And for the grid following, I only inject the P to the system. It's unit power factor control. For the grid forming, because I only guarantee my internal voltage at three-phase balanced, they need to provide the necessary P and both P and Q to guarantee my voltage. So they need to provide some Q, but unfortunately I didn't show them here before. But they are within their limit.
Yeah, not P and Q. Yeah. Current magnitude.
Current magnitude
is the value of the current by the grid forming inverter more than 1 per unit?
Sorry, what's that?
The value of the current injected by the grid forming inverter.
Yes.
Is it more than 1 per unit or 1.2 per unit during the transit?
Yeah, if you know P and Q, you know the voltage, you can easily calculate the current magnitude. I didn't show them here, but probably it's not 1 per unit.
So what I'm getting at is very likely what would have happened is that the grid forming converter, because it's a voltage source, and you didn't have, and I'm assuming here I may be wrong, because you didn't have direct limit on the current being injected, it injected as much current as the network required, right? And that's why you have a good voltage response.
Yes.
The moment you limit that current injection from the grid forming converter, the voltage will drop.
Yes, at a certain level, I believe you need to worry about your currents. But also a question, how do you design your inverter? Inverters need to have, you need to consider the P and Q, and also, yeah, okay. No problem. I agree. I know what you mean. So I think I already explained to you, and you also know what I explained to you, right? Okay.
Let me just make one comment. Can everybody hear me? What's keeping that from happening is reserve in PV. So it's sized for the maximum power point. It's operating often. So it has enough headroom without having over. And that's a very subtle thing in how you size these reserves and what value they bring.
Comment on that, I guess the question is how much reserve that has to be allocated, right?
And also the fact of if we keep the same amount of reserve and current capacity following inverter, then how does it
Okay, next question.
Thanks for the talk. I have two questions. Hopefully they're not too simple. So the first is, how would this compare to, for the voltage regulation, to just a conventional volt bar group control like we see in the standard now?
So you, okay.
Okay, yeah.
Okay, sorry, because if you ask two questions, I might not remember. So for the first question is volt bar, right?
Yeah.
So volt bar is kind of reverse QV, because volt bar it measures the voltage and change the Q, and the QV group is measures the Q and change the voltage. So here we didn't model that volt bar in grid following inverters, but we can also model that. But the question is, for the grid forming inverter, if you have QV group control, the purpose to design is QV group control is to avoid the sources. So people are thinking about volt bar. We didn't use it too much, because maybe I know some people use volt bar to maybe compensate the voltage violation issues. It might work. We can explore it, but here we didn't show the research.
I think this one's a simple question. Could you do this with single phase devices, or is it for YMD?
Yeah, this is a three-phase simulation, so we can definitely model the three-phase or single-phase in this system. It's already been done here.
Good question. So, as you rightly mentioned, actually, when you're looking at the controller, you're looking at when you're looking at grid following, especially, you're looking at positive sequence detection.
Yes.
So, what if you introduce actually a negative sequence control along with a positive sequence controller? Effectively, that's likely the means by which you have very good frequency response.
Yes.
In the grid forming mode, because in the grid forming mode, I'm assuming you're looking at the voltage being controlled, which means the current can be unbalanced. Second question is, when you say frequency, how are you defining the term frequency? Because this is not anymore an electromechanical term, it's more like, I'm assuming you're measuring somewhere near the inverter and then trying to identify what the frequency is.
Okay, so very good question. So for your first question, here we just inject a positive sequence current to the system. Actually, in the grid lab, you can do many different control methods. We can inject the negative sequence and inject the zero sequence. But based on our reading, according to the references, in this area, they complain that the inverter only injects the grid following inverter only injects the positive sequence to the system. Even during the fault, it still injects positive sequence current to the system. So here we just take that example. So you only inject positive sequence currents. Also, well, of course, if we can explore into the possibility of negative sequence currents, but here we didn't go that far. So it's a preliminary research. So that's a very good question. So, and also the second question is, how do we define the frequency, right? That's also a very good question, I believe. But here, the frequency, all I show here is the speed of the generator. So that's clear, right? I want to avoid to define the definite, the frequency, because that's a huge question. But here I just show the speed of the generator and use it to represent the frequency in this simulation.
This is not the inverter terminal.
So all I show here is the speed of the frequency. Other than the speed of the generator. Only in these slides, you can see during this trend there are three frequencies. One is from the generator speed. Another is the frequency from the PUF group controller. And the third one is we measure the frequency. We use a phasor lock loop to measure the frequency at load bank 4. During the transient, you can see they are different. So I want to avoid defining how the frequency. I just want to show you the speed. So that makes things clear, easier to understand, right? Okay.
Last question. All right, I get the last question. So as a non-expert in the converter area, is my takeaway accurate by saying, you should not try to be 100% grid forming. You have a percentage of grid forming, that's the ideal situation. Would you say that, or would you say, oh yes, I prefer to have 100%?
I really like your question, but I cannot say the answer because this is just preliminary research. So in our presentation, we only show the two extremes. One is all of the grid following, and all of the second case is all of grid forming. I believe we can definitely explore maybe 50% grid following, 50% grid forming. That's a open question, but now it's just the preliminary research we present here. So we hope we can have some support to go further in this area. So really appreciate your question.
Thank you very much, Wayne.
Okay, thank you.